What's up guys, it's me Sir Ernest, and today we will talk about the motion of particles in a rotating coordinate system. So here we're going to talk about pure rotation. So that means we're not going to consider the motion, the coordinate system that is translating. So just like what we discussed before, let's consider two coordinate systems. A fixed system. So let's say we have your z, x, and y. And then if we have a pure rotating system, so that means the moving system or the prime system or the rotating system has an origin that coincides with the origin of your fixed system. For example, at a given instant, the prime system rotates about some axis of rotation. So let's say at that given instant, the x axis is in this direction, the y axis in this direction, and the z axis is in this direction. And just like for our translating coordinate system, we're going to label our moving system with prime. So that means x prime, y prime, and z prime are the x, y, and z axis of a rotating frame. Okay, so let's say we consider a particle at point P. So from here we can define the position vector with respect to the fixed frame. So let's call this R. And because the origin of your moving axis and your fixed axis are the same, this the position of your particle with respect to the fixed axis would be equal to the position of your particle with respect to your moving axis and fixed axis. Okay, so let's say at this moment the rotation happens with a given axis. So that axis is designated by a unit vector n. Okay, so for example, that axis is in this direction. Okay, so that means this axis is your axis of rotation, and at this given instant, this is defined by your angular velocity. Okay, and let's say this at this moment we say that this is our origin, and the prime system would be, let's say here will be your x, this will be your y, and let's say this will be your z. Okay, so in this figure we can see that, as I mentioned earlier, that we're going to designate the direction of the rotation omega as n hat. So n hat is your unit vector along the direction of your axis of rotation. Also, the unit vector along the x, y, and z components or axis will be labeled as I prime, j prime, and k prime. So you will notice that as this axis rotates, the direction of I, j, and k primes also changes. So take note of that. So if we assign the instantaneous velocity to be omega, so therefore this is equal to omega n hat. And the sense of direction is provided by the right hand rule. So if the rotation is in this direction, the direction of your omega is here, and that is designated by your n hat. Okay, so since the coordinate system, since the particle at point P is designated with r and r prime, they are equal because the origin of the two coordinate system is the same. So we can now rewrite that as follows. So if r is equal to r prime, So therefore, x I hat plus y j hat plus z k hat is equal to x prime I hat prime plus y j hat prime, this is also prime, plus z prime k prime. So here we have two sets of unit vectors. The unit vectors associated with the prime system, which is not a constant, and the unit vectors of the fixed system, namely I hat, j hat, and k hat. And these are fixed. Therefore, these are constants. So if we're going to calculate this, so that means we have to, if we take the velocity of the particle, let's say in the fixed system, so that means this is derivative of r with respect to time. So in unit vector notation, this is now equal to derivative of x with respect to time I hat plus derivative of y with respect to time j hat plus derivative of z with respect to time k hat. And this is equal to the derivative of this. Okay? Because x prime and I prime are not constant. They change as a function of time. So therefore, we will use chain rule when differentiating this term with respect to time. So for this term, the derivative of x prime I prime with respect to time would be derivative of x prime with respect to time I hat plus x prime derivative of I hat prime with respect to time. And the rest will follow. Derivative of y prime with respect to time j prime plus y prime derivative of j prime with respect to time plus derivative of z prime with respect to time k prime plus z prime derivative of k prime with respect to time. Okay, so from here, this term and this term is actually the velocity of your particle relative to the prime system, which is this one. Right? Because this is x dot prime I hat prime. This is y dot prime j prime, and this is z dot prime k prime. So when you add them together, we end up with your velocity with respect to your relative to the moving frame. And then this term plus this term and plus this term, we just write it here. So this is x prime di prime dt, or derivative of I hat prime with respect to time, plus y prime derivative of j hat prime with respect to time, plus z prime derivative of k hat prime with respect to time. And this part would be your v. So v here is the velocity of your particle with respect to the fixed frame. V prime is the velocity of your particle with respect to your moving frame. And then this term is a velocity term, but this term represents the velocity due to the rotation itself, or the rotation of the prime system itself. Okay, this contains how the unit vectors change with time as the axis rotates. Okay, so in the next video, we're going to calculate what are these derivatives. And because of orthogonality, these unit vectors will be considered separately. So what we will do with the I prime component of this term would be followed by the j hat component and the k hat component. Okay, so that's all for now. So this sets up our next video, which is calculating how the unit vectors in the rotating frame changes with time. Okay, so for now, that's all. Thank you for watching, and I'll see you guys in the next video. Bye bye.